Hello everyone, welcome back to the CSA Guy. Today we are diving into some fascinating concepts in artificial intelligence, focusing on logic-based agents, logical reasoning, propositional and first-order logic, unification, chaining methods and resolution. So let's get started. First, let's explain the architecture of a logic-based agent. A logic-based agent consists of three main components: knowledge base, inference engine, agent program. Knowledge base is a collection of facts and rules about the world represented in a formal language. The knowledge base allows the agent to store information and reason about it. Inference engine is a component that processes the knowledge base to derive new information or make decisions. It applies logical rules to the facts in the knowledge base to infer conclusions. Agent program is the implementation of the agent that interacts with the environment. It uses the inference engine to process inputs from the environment and update the knowledge base accordingly. Now let's discuss how the Wumpus world exemplifies logical reasoning. The Wumpus world is a classical example used in AI to illustrate logical reasoning. In this grid-based environment, an agent must navigate to find gold while avoiding a creature called the Wumpus. The agent has limited knowledge about the world and must use logical reasoning to infer the location of the Wumpus and the gold based on the information it gathers. For instance, if the agent enters a square and detects a stench, it can infer that the Wumpus is nearby. The agent uses its knowledge base and inference engine to make decisions about where to move next, demonstrating logical reasoning in action. Next, let's compare and contrast propositional logic and first order logic. Propositional logic deals with whole statements that can be either true or false. The syntax consists of propositional variables like p, q, and logical connectives and or not. For example, the statement p and q is a propositional logic expression. First order logic, on the other hand, extends propositional logic by allowing us to express relationships between objects and quantify over them. The syntax includes constants, variables, predicates, and quantifiers. For example, for all x, human of x to mortal of x means for all x, if x is a human, then x is a mortal. Semantics also differ. In propositional logic, the truth table of a statement is determined by the truth values of its components. In first order logic, the truth of a statement depends on the interpretation of the objects and relationships in the domain. In summary, while propositional logic is simpler and deals with whole statements, first order logic is more expressive and can represent complex relationships and quantifications. Now let's describe the process of unification in first order logic. Unification is the process of making two logical expressions identical by finding a substitution for their variables. It is a crucial step in inference, allowing us to apply rules to specific instances. For example, consider the two expressions human of x, Socrates of human of Socrates. To quantify these expressions, we can substitute x with Socrates. This means that the two expressions can be made identical through this substitution. Let's look at a more detailed example of how unification works in inference. Suppose we have the following two statements. For all x, human of x to mortal of x, all humans are mortal. Human of Socrates, Socrates is a human. To infer mortal of Socrates, we first unify the first statement with the second. We substitute x with Socrates in the first statement, resulting in human of Socrates to mortal of Socrates. Since human of Socrates is true, we conclude mortal of Socrates through modus ponens. This illustrates how unification facilitates logical inference. Next, let's explain forward chaining and backward chaining. Forward chaining is a data-driven approach where we start with known facts and apply inference rules to derive new facts until we reach a goal. For example, if we know All humans are mortal. For all x, human of x to mortal of x, Socrates is a human, human of Socrates. We can use forward chaining to infer that Socrates is mortal, mortal of Socrates. Backward chaining, on the other hand, is a goal-driven approach. We start with a goal and work backward to see if we can find supporting facts. For instance, if our goal is to prove that Socrates is mortal, we check if Socrates is a human, is true. If it is, then we then check the rule all humans are mortal to confirm the goal. Scenarios. Forward chaining is preferable when we have a lot of known facts and we want to derive new information. Backward chaining is a more efficient when we have specific goals and want to confirm their validity based on existing knowledge. Finally, let's define resolution in first order logic. Resolution is a rule of inference used to derive a contradiction from a set of clauses, allowing us to prove the unsatisfiability of a set of statements. It works by taking two clauses that contain complementary literals and producing a new clause that combines the remaining literals. Example, consider the following two clauses: human of Socrates or mortal of Socrates. If Socrates is not human, then he is mortal. Human of Socrates, Socrates is human. To apply resolution, we can resolve these two clauses on the literal human of Socrates. This gives us the new clause, mortal of Socrates. This process can be repeated with other clauses to derive further conclusions or contradictions, demonstrating how resolution can be used in logical reasoning. That wraps up our discussion on logic based agents, logical reasoning, and various logical frameworks. I hope you found this information helpful and insightful. If you enjoyed this video, please give it a thumbs up, subscribe to CSE Guy for more content, and leave your questions or comments below. Thanks for watching and see you next time. Thank you.